20 to 80 business. Okay, so everybody has a set of cards 20 to 80. So what you're going to have is you're going to have a number line up on the board. Or on the overhead, or on the Elmo, or whatever.
Yeah.
You have an Elmo?
No.
Whatever. You'd have this all prepared, okay?
Mm-hmm.
Okay, so they go and they do the stretching out and whatever, you give them time to do that, they kind of pair them off and they get the middle number. All you do is come up and put that line there, okay? Now what you tell them to do is stretch them out again. Take all the ones below the middle number, take all the ones above the middle number. Play the same game with those.
Okay.
So now, what's going to happen is, okay, so suppose the median turns out to be 48. They play the same game again, and the lower number is going to be, yes, what's the lower number? Somebody's going to say 33, yeah, 33, and you say, okay, let's put a 33 there, and say the higher number is 67. So you put a 67 there, and just draw your box.
Okay.
Okay? If you want to then give them another set of cards, or maybe then just give them a set of data with numbers, okay? And then what you do is you say, okay, now look at your list, look at your what's the lowest number, and what's the highest number? And then say, okay, now what we call this is a box and whisker plot, you know, just define it,
Mm-hmm.
and then talk about these numbers. Initially, I would write the numbers in just to make sure that they understand whatever's going on. Then what you could do is you could ask some analysis questions in terms of, okay, so, and you know the numbers in the set because you wrote them, okay?
Mhm.
Suppose the number, in the set there's the 42. Suppose that 42 became a 38. Would that change anything in the graph? Would that change, you know, so you get this idea of motion. Like with the mean it would, but with the median it doesn't. It might not, okay?
Right.
Then what you can talk about is something that comes up in what the guys are talking about, is this, okay, so between here and here, oh, I'm sorry, I'm jumping ahead. Then what you do is you have them count the number of cards between 23 and 33, the number of cards between 33 and 48, the number of cards between these two, and the number of cards between these two. And it's going to turn out to be 1/4 of the cards. Then you introduce the term quartile,
Okay.
okay? And this is the first quartile, this is the second quartile, the third quartile, and the fourth quartile. As areas, not as, now,
Right.
statistically, we call this the first, you know, when somebody says what's the first quartile, the person might say 33. But actually, this represents the end point of the first quartile. That's what people never talk about, you know. The 33 is not the first quartile, it's the end point of the first quartile. The 48 is the end point of the second quartile. The 66, 67 is the end point of the third quartile. And this, so the idea is that the quartile is not a single number, although that's the way we refer to it, you know. It actually represents all of these, and you get the word quartile, not so much by just introducing it by talking, but by actually talking, having them see that the data is actually broken up into approximately 4. Now, if you want to do a really neat job, what you do is you set up the card so it exactly comes out to be 4, because the first one is good. You know, with that random experiment we did, or you did the other day, sometimes that doesn't come out as neat. You might have 6 kids in one and 7 kids in another and all, and you have to kind of approximate. But with setting up the cards, it should come out. And they won't, I don't think they'll even realize the cards are set up, you know, set up job or anything like that. So now we've done median, we've done quartile, we've done outliers. Then what you could say is, okay, what numbers, or what is the range of the quartile? And that's a problem, because sometimes when you say range to people, they'll say 33 to 48. That's not really accurate. Statistically, the range means that this is going to be 15 points, or 50, you know, you could say these cards represent grades. They'll understand that. So this is 15 points, this is 10 points, this is 19 points, and that's 12 points. Okay, so the range, what they call it, the interquartile range, right? Or actually, it should be intraquartile range, unless I'm misinterpreting it. So this would be, So then you just start talking, now, how long this takes, this could take a day or two. In other words, you could give them the cards, do so much, maybe do this, give them the data, have them do their own box and whisker. Come back maybe and give them a couple of things to do, is come back the next day, give them the same set of cards back, have them lay it out, and now start talking about what we call this the quartile and all that stuff. So it's kind of like layering, like they really get good at drawing box and whiskers. Let's not run over them with everything. Let's just talk about box and whiskers for a day and then come back and talk about quartiles and then come back and talk about maybe they can take the range for a day and, in the same day they can take the range. You have to be the judge of that.
Okay.
But that's kind of the schema of median, box and whisker, quartile, kind of do it and then introduce it. Okay? And that would just be a matter of I would get small index cards or I wouldn't use, maybe get small index cards and with a paper cutter, cut them in half so you get squares, but they're a cardstock, not the paper that you were using. Okay?
I like that.
So what you're saying is we can trust that lots of the data lands here, and that these things really can skew the data one way or the other.
Well, yeah, what it's, the way I've always seen it applied is you take 1.5 times, like that's 33 to 67, so that's 34.
Right.
So you take 34, multiply by 1.5, and then
So that's 51.
and then figure out what 51 is. 51 plus 67, and any data point that you get
Beyond
that
Oh,
is
okay.
what is considered an outlier and should be checked and to see if it's just an anomaly or if there was some sort of bad entry.
All right, so we did this, and if we were to take this, multiply it by 1.5, we get something way out here, we know that this is fine. In other
Right,
words,
well,
this is relatively good data then. There's nothing that's going
Right.
to, as I said, skew the
Yeah,
data.
right.
And the same thing here, assuming that, we had numbers less than 20, take this 1.5 the other way. Okay.
Yeah. So in fact, in this example, there's no possibility of an outlier to the low end because you can't, unless you're dealing with data that can be negative, I suppose. But,
Okay.
Yes, so it'd be 51, or
33 minus 51,
exactly.
that gives you your lower bound of non-outliers. 67 plus 51 gives you your upper bound of non-outliers.
Okay. So these then are not considered outliers, they're just considered the lower data point and the higher data
Right.
point.
And they,
Lowest and highest data.
yeah, depending on how big they are, they could
Yeah,
be
those-
outliers or they could not.
Okay.
An outlier is a data point that does not belong, like 269, 408.
Right.
They
Right.
just like that. They want you to know that that's an outlier. So they were tested on that last year. It was just like
Yeah, there was
Yeah.
one which was just like, these are the points by a basketball team, and they had, these guys like scored 40, 46, 49, and then one guy scored 98 points, which would be a better indication of the average, the mean or the median. So like most of the kids were able to say, well, the 98, it's an outlier, but because it just didn't make sense to them, like most of the team is scoring about 40 points, but that was their notion of outlier, just something that is
Something skewed.
exactly, not really based on a formula.
And it's my understanding too, there's no agreed upon formal definition of what an outlier is. It's just, like a lot of statistics, it's kind of this ethereal place where you say, well, this is,
this one.
Which is my problem with statistics being brought into the school
Yeah.
level, because with the school level, especially with the type of testing that's done, especially when it's standardized and when it's multiple choice, the ethereal doesn't play a role here, it has to be, and the question is, would 480 be considered an outlier?
Right.
Well, statistically, yes, and common sense, yes, but,
Maybe mathematically.
mathematically, does it really make any sense in terms of why this thing is called an outlier? And so, it gets into all kinds of, but it's still the problem I always have had is it's still in the curriculum.
right.
Thank you.
Yeah,
That's
okay.
really good. That's really good. That makes a lot more sense than the way they interpret it.
I mean, if the example was, for instance, age of a certain population.
Mhm.
Would be, someone between 0 and, 90 years. But someone who's 120, which may be the case, that would be totally an outlier for us. 128 years is not something you go for. But in mathematically,
Yeah.
it's fine. So,
Yeah, that's right,
depends on the data set that you're looking at.
Sean, that's something else you might want to do is instead of those cards being grades, which could be depressing because you have grades from 20 to 80, have them be, and this is what I do with my classes, have them be, they surveyed 25 people, okay, say you have 25 cards. They surveyed 25 people, this is the age range they got. These are all the ages of the 25 people, okay? What you can then do as a follow-up activity is give them all different cards, different sets of cards, and then where the age ranges are different, and then start talking about, okay, here's an age range where it seems this group is younger than this group. What would happen in terms of the social needs of this group? As who would need more schools? The people 35 and above, or the people 20 to 35, and that type of thing. To really get, they start talking about real world experience, real world problems as opposed to fake world problems.
Okay.
How hard would it be to ask each of the students to record their height in inches and make a box and whisker plot of their heights in inches? Because then they've got an actual connection to it themselves. They can be like, oh, that data point is me.
Or shoe size.
Or shoe size would be another great, anything.
I
you
think
can
the idea of
add in.
size and inches would be good, but I think to get a data set, take a day, just a piece of a class,
Mhm.
put a chart up, excuse me. The chart is 4'5" to 6'2".
Mhm.
Yeah, that one guy in class is 7'9". He's big.
It's pretty tall.
Nice kid, but very tall. And have them actually take a card, okay, and just put, okay, take the table. I know I'm 5. Most kids don't know how many inches they are.
Mhm.
I'm 5'6".
Right.
I just look up at the table, 5'6". Okay, I'm that many inches. Hand the card back in.
Yeah.
Do that for all your classes.
Mhm. Mhm.
Now you have a set of cards. Now
Yeah.
you have a set of 100-something
Yeah,
cards.
I say it's that.
And then what you can do is duplicate those sets, or whatever you want to do with them,
Mhm.
or maybe just cut them in half and make them 2 different sets. So I randomly cut my classes in half. Let's look at the sizes that we get, and just come up with creative things to do once you give them the data. But the idea of the feet to inches, I would say here that would be almost in a sense like you want to use it as a vehicle. It becomes the lesson, because
Right.
they're going to say, okay, so you have to multiply the number of feet times 12 and then add, multiplying the number of feet times 12 for some kids is going to be
Yeah.
a challenge. And so, and you don't want, what we've tried to do is not get into that stuff.
Not
Not that we don't
not have
want
a
kids to
lesson
be,
within a lesson.
right,
Yeah.
don't do something as a vehicle that creates like the do now.
Yeah.
Many times the do now, you try to just do something, and all of a sudden, 30 minutes later, you're still doing the do now.
Yeah.
That's what we've tried to avoid.
Yeah. No, that's a good idea.
So 7n plus -4 equals, say, -12. And they know enough to add 4 to both sides, okay? Okay, now the question comes up, well, what's -12 plus 4? Well, that's at the beginning of 9th grade. That, in a sense, is a skeet shoe. It could be anywhere from +16 to -16, okay? And somewhere in the middle is the correct answer. And you'll have kids in your class doing this. If you did this, I don't know what to do, 125. Most kids are going to do this, most kids are going to do this, and most kids are going to get a correct answer. The only thing that's screwing them up, if I may put it that way, in the algebra is not the algebraic structures, it's the number set that we're teaching the algebra with. because they don't understand the integers. And unfortunately, there was a major, what was it called, the Math Advisory Council 3 years ago, national group, said we have to teach out integers and fractions better so the kids can learn algebra. My idea is no. My idea is you don't deal with integers and fractions. You teach the algebraic structures, they overlearn that, so that when it comes time to do it with the integers and fractions, they're ready to do it. And that seemed to work very well last year with Ghislaine. It's worked very well at Manhattan Hunter, where we've used it for 5 or 6 years now. And
Can you bring that screen down?
Sure.
Okay, so when, in these lessons that we're following, when these different pages are put in, that we can go and like get, use certain examples or get, all right. What I've been doing is what I thought was coming from this and going to the book and pulling out problems for more practice. But we're, they're not, they're running into the -12 over there adding.
right, and you don't do those. And if it comes to the fact, and talk to Ghislaine about this, because she's gone through this for at least a year now. If it comes to the fact of not using the book and making up your own 12 problems or whatever, then you do that. I mean, that's not a big issue, just making up 12 equation problems. Okay? And one of the things maybe we should think about doing in the future with this project is actually adding those pages. Like for example, if Shonda does this and says, well, the book doesn't help, so I'm going to make up my own set of 10 equations. And the rule is, if you're doing something, you add it in, and everybody else knows about it. So then she just slides that in. She sends a copy to everybody and says, this is what I used to practice during lessons 6 and 7. Use it if you want. If you want to make up your own, that's fine. So 5 years from now, when more new people are in, and they come to this point, they say, oh, it doesn't work in the book. Oh, but wait a minute, here's a worksheet that a practice sheet that the curriculum provides. That's the way we grow this thing.
And spread the work around.
And spread the work around. Because she may not be there yet with some lessons. She may be ahead of you, she may be behind you. So as you fill in for your lesson, you're handing stuff to her that she can use with her lesson, and vice versa. And that's the way you play the whole year.
How long do you belabor showing tiles and balances if they're not getting it? How long do you continue?
That's your judgment call. I can't tell you what to do there. That's something that comes from actually experience in the classroom. The point is, if they're not getting it with tiles and balances, then don't move on from there. Pick up something else in the curriculum. Don't continue to do. Some people say, well, they're not getting it with tiles and balances, so I'm just going to do it symbolically. They don't get it symbolically either, so there's no sense in doing that. So maybe do the median, maybe do the mean. That's why if you look at so for example, suppose you get in here and you're really hitting a wall. Then you go here. Just make a note that you didn't do this yet. Okay? And this can be done and then go back to here. So you might do A, B you hit the wall with, they're having a problem with that. So you do C and possibly start into D and then go back and do B. And my thinking is, the psychology behind this is, if you do parts of B and they don't get it, when you come back to do it, if you haven't pushed it too hard, when you come back to do it the second time, there's going to be a better reaction on their part to it. It's like that thing of I didn't learn it the first time, but all of a sudden the second time was a lot easier to learn for some reason. Well, it's been banging around in your head even though they didn't realize it. This is a system that I devised for the teachers in terms of problem solving. I also used this myself when I taught the Algebra 1 course for college students. So this was not a college algebra course. This was Algebra 1 for college students. These people had either failed algebra, had never taken it, whatever. And so this is the system I used in terms of developing problem-solving skills. And when I say problem-solving skills, I mean the typical algebra problem. The first thing we did was we solved arithmetic problems. The difference between an arithmetic problem and an algebra problem is the following. This is an arithmetic problem. you're given some kind of number and some kind of thing, and you're given another kind of number, another number, and another thing, and you have to find the total. So for example, you're given a number of CDs and a number of computer games, and you have to find the total. In an arithmetic problem, you're given these 4 items, and you have to find that, okay? This is arithmetic. In an algebra problem, what happens is you have the same structure, except you're only given 3 of these things and the total, and you have to find the 4th thing. So if you have to find the total, it's an arithmetic problem. If you have to find one of the 4 items under the total, except and not the total, it's an algebra problem. And so, however, what we have to look at is that the structures of those problems are exactly the same. So if you look at numbers 1 and 3, Sasha bought 6 CDs for $7 each and paid $9 for the shipping. What was his total bill? Okay? Now, you're going to have to counsel kids on this, because one of the kids in my class, one of my college kids, said, well, let's see, I multiply the 6 times the 7 and I get 42. And I multiply the 6 times the 9, and I get 54, and I add them together, and I get my total. And I was like, well, if I ever start a mail order house, I want you on my list, because I'm gonna make lots of money. And he had no idea that 9 was a constant, okay? So so that's one structure. Now look at number 3, it's exactly the same structure, except now, what we have is, so let me write up the first one. So the first one would be 6 times 7 plus 9 equals the total. In number 3, it would be 4 CDs, the shipping cost is $7, so this is the arithmetic. This is the algebra. The shipping cost is $7. Okay, the total is $27. Shipping is $7, the total is $27. We're buying 4 CDs, and we don't know how much money we're going to spend. Exactly the same problem, okay? It's just a matter of the structure. The mathematical structure is different, okay? And I think what happens sometimes is we introduce algebra problems in such a way that the kids think that they're totally new to the scene. What I suggest you do is, before you go near a structure, an algebraic structure, is give them some arithmetic problems. You don't have to necessarily do this one, but for example, if you look at number 2, Mary bought 5 CDs at $6 and 3 computer games at $8. How much was her total bill? And then look at number 4. Number 4 is exactly the same thing, except we're not told how much the computer games cost, and we are told that the total cost of the purchase was $78. Same structure, except now we have to solve the equation. We have to solve the algebraic equation as opposed to solving the arithmetic equation. Because in that arithmetic problem there, we're actually solving the equation here at a very low level, needless to say, but this is solving this equation. Okay.
So are you using tiles, or what are you using?
Well, no, I'm just talking about the structure of the problems right now, how you do it. You know, if you want to use tiles, you can use tiles, and we can talk about how you do that. All right? Okay? What happens then is, if you look at 5, so that was 1 and 3, 2 and 4. If you look at 5 and 6, they are literally the same structure as 4, except there's a wrinkle. So, for example, the structure for number 4 is, she bought 5 CDs at $9 and 3 computer games at some money. Get rid of that. And the total was $78. That's number 4. The structure for number 5 was, she bought 6 CDs and 5 computer games. The computer games cost twice as much as the CDs. So you have the cost of the CDs here, and you have 2 times the cost of the CDs there. but it's still the same structure. That's number 5. Number 6 is she bought 6 CDs and 5 computer games, and in this case, and the total, I'm sorry, I didn't put the total in number 64. I'm given the total is 54. So she bought 6 CDs and 5 computer games. The computer game cost $2 more, so this is going to be there. Exactly the same structure. How you solve these problems mathematically is different, but the structure of the problem is the same. And what I found people doing was teaching each one of these as a different structure. And the kids were kind of like, well, what structure is this? What structure is this? What structure is this? They're all the same structures. But what really helps is if you start off with, for example, an arithmetic problem of this nature would be, she bought 6 CDs and 5 computer games. The cost of the CD was $8. The computer game cost twice as much. How much did she spend? So they have to actually realize that I'm only given 3 things, but I'm given clues to get the 4th. And that's exactly what happens here. I'm given an amount of money, whatever, for the computer game, for the CDs, and the computer games are twice as much. Down here, what I would do here is say, okay, she bought 6 CDs and 5 computer games. The cost of the CDs was $8. The computer games were $2 more. What is the total? In other words, use that same language structure in arithmetic problems and then use them in algebra problems. And that's what we don't do. What we do is we throw these structures at them and also expect them to be able to translate that into algebraic equations. And that's where they go off. So you'll have a kid who will be able to do something like, 5 CDs at $7, and let's say 5 CDs at $7 and 6 CDs at $9, or computer game and find the total. They'll be able to do that. They won't even be able to set up this structure because it's foreign to them. They don't see it as being a similar structure to what they've done.